Hello students. So today the topic that we are going to discuss a new chapter, moving charges and magnetism. NCERT section 4.1 to 4.2 and example 4.1 to 4.2. This is disclaimer. So the strategy for competitive exams for this chapter. So you have to start by drawing clear diagrams showing the direction of motion, fields and forces accurately. Okay, so in this chapter there is a major challenge to determine the directions of the forces. Okay, because we are going to discuss about the all the dimensions in the three dimension: forces, magnetic fields and motion of a charged particle in three dimensions. So the direction of force has to be found accurately. Always be clear about the right hand rule application. Okay, what is right hand rule? We are going to discuss. Focus on understanding vector relationship and cross products, because cross product we are going to use in this chapter, and as they appear frequently in magnetic force calculations. Practice recognizing patterns in similar problems and learn to spot shortcuts for faster calculations. Memorize key mathematical expressions, but more importantly, understand their physical significance. And develop the habit of checking units and dimensions as a way to verify if your approach is correct. And please visit https://forum.pruter.ai for book recommendations and guidance. So what are the learning objectives from this topic? Define the fundamental relationship between electricity and magnetism, to calculate the Lorentz force on a charged particle in magnetic field, to determine the force experienced by current carrying conductor in a magnetic field, to understand the right hand rule for determining force directions, to identify practical applications of electromagnetic forces in everyday device, and apply basic electromagnetic principles to solve simple force problems. So the index, the topics that we are going to discuss today is NCERT section 4.1 Introduction, NCERT section 4.2 Magnetic Force, and in 4.2 section there are sub sections, 4.2.1 Sources and Fields, 4.2.2 Magnetic Field Lorentz Force, 4.2.3 Magnetic Force on a current carrying conductor. Then example 4.1 and then example 4.2. So let's begin with the introduction, NCERT section 4.1. So people knew about electricity. Okay, there was lightning about for a long time. Okay, so lightning was there since the very old times. So people knew about electricity. Okay, for about 2000 years. Okay, so they also know about magnetism. Okay, there were magnets in the old times, in the medieval times, like magnets attracting iron. Okay, they didn't know the concept that why magnet is attracting the iron, but they knew about this thing that this is magnet and this magnet is attracting iron and some other metals like nickel or cobalt. Okay, so they knew about magnetism unconsciously, not exactly knowing about the concept of magnetism. So they also knew about magnetism, like magnets and attracting iron, also for over 2000 years. For a very long time, everyone thought that electricity and magnetism were completely different things. Okay, so they didn't knew about the electricity and magnetism deeply. They didn't know about the deep concepts of these two phenomenon, and they also don't know that they are interconnected. They thought that electricity and magnetism were different things. So about 200 years ago, scientists discovered that electricity and magnetism are actually connected. How? This discovery showed that electric currents can create magnetic fields and magnets can create electricity. Okay, so about 200 years ago, scientists discovered that these both phenomenon are actually connected. Okay, so they are not different. So this the discovery of this interconnection of these two phenomenon showed us that electric currents can create magnetic fields and magnets can create electricity. So electric currents can magnetic field. This thing is moving charges and magnetism. This is the chapter we are going to discuss. We are starting today. Electric currents can create magnetic fields. This is the phenomenon of moving charges and magnetism. That thing we are going to discuss today. And this magnets can create electricity. This is the electromagnetic induction. Okay, we are going to discuss. This is chapter number 6 of your 12th class. Okay, so we are going to discuss it later. So this understanding led to many modern technologies we use today. Okay, so this understanding that these both things are connected and through electric currents we can generate magnetic field and through magnets we can create electricity. Due to this understanding of this two phenomenon, many modern technologies we use today, this interconnection or their relation of electricity and magnetism is used in that technologies. So how scientists discovered that they are actually connected, electricity and magnetism? During a lecture in 1820, scientist Hans Christian Ørsted noticed something interesting. What he noticed that when electricity flowed through a wire, okay, he was doing some experiment or giving a lecture in classroom in 1820. So he noticed that when electricity is flowing through a wire, then a compass needle is placed near that wire and it is showing deflection. Okay, so he noticed that when electricity flowed through a wire, it made a nearby compass needle move. Okay, so there was a deflection in the compass needle when it is placed near a current carrying wire. So this simply observation showed that electricity and magnetism were connected, because compass needle only shows deflection when there is a magnetic field in that region. Okay, so it is placed near the current carrying conductor. Okay, when there is no current from the wire, its deflection is, what is the default alignment of the compass needle? Its north end is towards Earth's north and its south end is towards south pole of the earth. Okay, this is the default alignment of compass needle. And all the magnets have default alignment in the direction of north and south. Their north will point towards the north, their south will point towards the south of earth. Okay, so this simple observation showed that electricity and magnetism were connected. He investigated this phenomenon further through various experiments. Okay, so this is just an observation at that time, but he investigated this thing through various experiments. So what was his observations after he did many experiments regarding this, and he listed some observations. So this is the diagram A and B, figure 4.1. So the magnetic field due to a straight long current carrying wire. Okay, there is a current carrying wire. So in A diagram, at the center there is a dot, and in B diagram there is a cross. Okay, so these are the sign conventions. This dot is representing current flowing through a wire. In which direction? Outwards and perpendicular to the plane of paper. Okay, or plane of screen. You are seeing a screen of mobile or laptop. So a current that is coming out of the mobile screen, or if you are seeing this diagram in a notebook, so coming out of the paper and perpendicular to the plane of paper or perpendicular to the plane of screen. Okay, so this dot is representing the current coming out of the screen or paper perpendicularly, and this cross is representing the current going into the screen or into the paper perpendicular to the plane. Okay, these sign conventions we are going to use in our whole chapter. So you have to remember, dot is representing outward direction. Current is coming out of the plane of paper perpendicularly, and cross is representing current is going inwards into the plane of paper perpendicularly. Okay, so figure 4.1 is showing the magnetic field due to straight long current carrying wire. The wire is perpendicular to the plane of paper. A ring of compass needles surrounds the wire. Okay, you can see there is a ring is formed due to the needles. The orientation of the needle is shown when the current is flowing outwards in A diagram. The current emerges out of the plane of paper, and B diagram is showing the current moves into the plane of paper. Okay. Now, what was the observations? The needle aligns itself like it's following a circle. Okay, you can see in the A diagram. In both diagram there is a circle, but you can see in the A diagram that shaded part with blue color is north of the compass needle, and the empty part, white part, is south of the compass needle. Okay, so this compass needle, when we place around this wire, it is aligning itself in the form of circle. Okay, this is one needle only. We are placing it at different positions around the wire, so it is forming a circle. So needle aligns itself like it's following a circle around the wire, with the circle being perpendicular to the wire. So wire is coming outward and perpendicular to the plane of paper or plane of screen, and circle is on the plane of screen. So this circle is perpendicular to the current direction. Okay, so the needle aligns itself like it's following a circle around the wire, with circle being perpendicular to the wire. Got it? As shown in the figure 4.1a. Now the effect is noticeable with large currents. Okay, if the current is weak, there is a weak current in the current carrying conductor, then this effect will be much less, and you cannot determine accurately the deflection of needle. So you have to use large currents, or you have to place the needle very close to the wire, because the magnetic field produced by this wire is strong near the wire, and after if we are going farther away from the wire, this magnetic field is becoming weak. So effect is noticeable with large currents and when the needle is close enough to ignore the Earth's magnetic field. Okay, so you all know that there is a magnetic field of Earth, natural magnetic field of Earth. Okay, so this magnetic field is very much less than means at poles the magnetic field due to Earth is very large, but away from the poles the value of Earth's magnetic field is weak. Okay, so to ignore that weak Earth's magnetic field, we have to place the needle very close to the wire, or there must be a large current in the wire, so that the magnetic field produced by wire will be very much large than Earth's magnetic field, so that we can ignore the Earth's magnetic field. So reversing the current direction reverses the needle orientation. You can see in the B diagram 4.1b, we have reversed the direction of current. In A, current is coming outward the plane. Now in B, current is going inward the plane. Okay, now reversing the direction reverse needle orientation. You can see in A diagram, north is pointing towards if we move anti-clockwise direction. So north is pointing in anti-clockwise direction, but in B diagram, north is pointing towards clockwise direction. Okay, so reversing the current direction reverses the needle orientation. Okay, so there is electron flowing through the conductor. Okay, so what is the effect of charge we will discuss, but in the conductor there is electrons only. So due to which the field direction is this. Okay, arrangement of iron filings around the wire. So this is the C diagram of 4.1 figure. The arrangement of iron filings. What are iron filings? Iron filings are residual iron powder, or very small small components or waste of iron from many processes, like if we are making something from the iron, then after furnishing it or polishing it, there is a very small dust or powder of iron. So these are called iron filings, or very small components. Okay, so these are iron filings. So if we place the iron filings around a current carrying conductor and shake it, if we are placing it at a table, okay, so we have to tap the table a few times so that this iron filings can arrange themselves according to the magnetic field around a current carrying conductor. So the arrangement of iron filings around the wire, the darkened ends of the needle represent the north poles. Okay, that thing I have mentioned, that the shaded part is north pole and the white part is south pole. The effect of Earth's magnetic field is neglected. Okay, because the Earth's magnetic field is very weak away from the poles, so it can be neglected. So arrangement of iron filings you can see. So around a current carrying wire, the iron filings are in the form of, arrange themselves in the form of concentric circles. So deflection increases when large current is flowing through the wire. Okay, that thing I have also mentioned, that deflection of the needle will be significant when there is a large current flowing through the wire, and when needle is much closer to the current carrying wire. And next thing is, iron filings spread around the wire form concentric circles. Okay, you can see in the figure 4.1c. So when we place the iron filings around a current carrying wire and shake it, or we can arrange themselves or give some time to arrange themselves, or to stir with the help of some rod or something, so that they can arrange themselves around a current carrying wire. Okay, so they will form a concentric circles around the current carrying wire. It means that magnetic field lines around the current carrying conductor is in the form of concentric circles. So the discovery led to the understanding that moving charges or current produce magnetic field in the surrounding space. Okay, this discovery tell us that currents or moving charges, because in currents moving charges are electrons. Okay, so moving charges or currents can produce magnetic field in the surrounding space. After Oersted's discovery, many experiments were conducted by various scientists. James Maxwell unified the law of electricity and magnetism in 1864. Okay, so all the laws that we have studied in electricity and we are going to discuss in magnetism, Maxwell unified these laws and made 4 equations, which we also know as Maxwell equations. We will discuss it in electromagnetic waves. Okay, so James Maxwell unified the laws of electricity and magnetism in 1864, proving that light consists of electromagnetic waves. Okay, so James Maxwell unified the laws of electricity and magnetism and discover the phenomenon of electromagnetic waves. Okay, so proving that light consists of electromagnetic wave. This thing we are going to discuss in detail in that chapter. So by the end of 19th century, Hertz discovered radio waves. J.C. Bose and G. Marconi produced radio waves also. So radio waves are also electromagnetic waves. So in this chapter, we will see how magnetic field exert force on moving charges and current carrying wires. Also, we shall learn how current produce magnetic fields, we shall see how charged particle can be accelerated to very high energies, and we shall study how currents and voltages are discovered by the galvanometer, or detected by the galvanometer. So in this and next chapter on magnetism, we will follow the following conventions that I have already mentioned. What are these conventions? This figure again. So for current or field, for both current and field, coming out of the paper's plane, if current or magnetic field, or you can say electric field also, if current or magnetic or electric field is coming out of the paper's plane, it is represented by dot. And if current or field going into the paper's plane, then it is represented by cross. And this current or field should be perpendicular to the plane. Perpendicular to the plane, it is always perpendicular to the plane. But cases for coming out of the plane, it is represented by dot. For going into the paper's plane, it is represented by cross. It is also represented in A or B diagram. Now 4.2.1 sources and fields. When two electric charges affect each other, it happens in two steps. Okay, we are going to have a recap of electric field also. Okay, so we will relate electric field with magnetic field. So when two electric charges affect each other, so many things, many concepts of this chapter are similar to the electrostatic. Okay, so in electrostatic we discussed electric field. In this chapter we are going to discuss magnetic field. Okay, so many of the terms are analogous to each other, so we will draw the analogy with that chapter also. So we will relate the magnetic field with electric field also. So when two electric charges affect each other, it happens in two steps. Okay, first step is, first charge create an electric field. There are two charges in the space, then first charge will create an electric field around it, and the other charge, the second charge, will experience the force due to that electric field. This thing we have discussed in that chapter, that first charge is like source charge and test charge. Source charge is producing electric field, and the second charge, we can say test charge, will experience force in that electric field. Okay, first charge creates an electric field around it, and this field then acts on the second charge. It is like throwing a rock in the pond. Okay, this is the some analogous. We are drawing the analogy. It is like throwing a rock in pond. The rock creates waves. Okay, like electric field. You can assume waves as electric field. Okay, and these waves, you can assume that rock as first charge, and this rock is creating waves in the pond, and these waves can be considered as electric field. Now these waves can affect the other objects flowing on the water. So there are some other objects that are floating on water, so we can assume that as other charges. Okay, or some object as second charge. So these waves then affect the objects floating on the water, like the second charge. Okay, you may have understood by this analogous. Okay, now mathematical part. A source charge Q produces an electric field E, expressed as, what was the electric field due to a source charge? E is equal to Q by 4 pi epsilon naught R square, and this R cap is the direction, unit vector, which is showing the direction of electric field. Mark it as 4.1. Now where R vector, R cap is the unit vector along the R. What is R? Position vector from the source charge. If we want to find a electric field at some point, so we have to draw the position vector from source charge to that point. Okay, and the R cap, unit vector of this position vector, is showing the direction of electric field. So where R cap is the unit vector along R, position vector from source charge, creating a vector field. A charge Q, now electric field is produced. Now this charge Q, a charge Q interacts with the field. Another charge Q is there, small q. We can consider it as test charge also. A charge small q interacts with this field, experiencing a force F, which is given by F is equal to Q into E. So what is E? Capital Q by 4 pi epsilon naught r square. So small q capital Q upon 4 pi epsilon naught r square and r cap, because direction of force is same as electric field. Mark it as 4.2. So we are having a quick recap. The electric field is a physical thing, not just a mathematical idea. Okay, it is not a imaginary or virtual concept that is just imagined by the scientist. It is a physical thing that really exists. Okay, so it is not invented, it is discovered. The electric field is a physical thing, not just a mathematical idea. It can carry energy and momentum. Okay, if it is virtual, then it will not affect the real things, but it is affecting the charges and also transferring the energy and momentum. So it is a physical thing, not just a mathematical idea. Okay, so it can carry energy and momentum to one place to another. Okay, so if we place any charge in the electric field, it will experience force. Due to force, it will displace. Work is done, means energy is transferred. So these electric fields can carry energy, and also electron or any other charge is feeling force, it will move, kinetic energy will change. Okay, so it is carrying momentum also. It is carrying momentum and energy both from one place to another. Travel through space at specific speed. Okay, so this electric field is traveling through space at specific speed, which is the speed of light. This understanding was first developed by scientist Michael Faraday. It later became an important part of James Maxwell's theory that showed electricity and magnetism are connected. Okay, so electromagnetic waves, by the name electromagnetic waves. So in electromagnetic wave, there is a electric field also, magnetic field also. Okay, so by this both chapters, current, electricity, electrostatic and magnetism, they all are connected. Okay, so after these all the discovery of these topics, James Maxwell unified the laws of electricity and magnetism, and then developed the idea of electromagnetic waves. Okay, so it later became an important part of James Maxwell's theory that showed electricity and magnetism are connected. Think of it like throwing a ball. Okay, the point I have mentioned that it carry an electric field is carrying energy and momentum, and it is traveling through space at specified speed. So we are explaining this thing with the help of this example. Think of it like throwing a ball. The ball takes time to reach its target and can transfer energy when it hits something. Okay, electric field is doing same thing. When it hit any charge, it is transferring the energy to that charge in the form of work done. Okay, or in the form of change in potential energy or change in kinetic energy. Similarly, an electric field travels through space and can affect objects, or especially charges it encounters. So electric field can vary with time. Though our present discussion assumes time independent fields. Okay, so electric field can vary with time also, but in this chapter we are discussing about only time independent fields, which are not dependent on time, but it can vary with time. Multiple charges create field that add vectorially according to vector algebra. Okay, so we have discussed the principle of superposition principle, or principle of superposition, according to which multiple charges can create the fields at a point. Okay, we can find the force on a charge due to number of charges around it. We can find the electric field at a point due to number of charges around it, according to principle of superpositions. According to principle of superposition, multiple charges create fields that add vectorially. That is according to vector algebra, because electric field is vector. So we have to do vector algebra, not simple sum up, following the principle of superposition. Once the total field is determined, the force on a test charge followed, F is equal to QE. Okay, this is field due to multiple charges at a point. Now, similar to static charges producing electric field, currents or moving charges generate a magnetic field. Okay, as we have discussed that static charges produce electric fields. Similarly, currents or moving charges, we can say. In currents, there are also moving charges, electrons. So currents or moving charges generate a magnetic field. It is represented by B. Like an electric field, a magnetic field can be measured at any point in space. Okay, so similar to the electric field, magnetic field can be measured at any point in space and can change over time also. Okay, it can vary over time also. So think of it like an invisible force that surrounds magnets and can vary in strength depending on where you measure it and when you measure it. Okay, so we have mentioned that magnetic field can be measured at any point in the space. Okay, so according to this, if there is an invisible force that surrounds the magnet, okay, so the strength of this force can depends upon where you measure it. Okay, near the magnet, near the poles, away from the magnet, it depends on that thing, but can be measured at any point in the space. Also, magnetic field can be changed over time or can change over time, means when you measure it. It is depending on when you measure it. You are measuring now, after 2 seconds, after 1 minute, so it can depend on time also. Okay, but in this chapter we are generally discussing about the time independent fields. Okay, magnetic fields can obey the superposition principle. Like electric field, magnetic field also obey the superposition principle. That is, the magnetic field due to several sources that are producing the magnetic field. So magnetic field due to several sources is the vector addition of magnetic field of each individual source. Magnetic field is also vector quantity. Okay, like electric field, magnetic field is also a vector quantity. So magnetic field due to several sources is the vector addition of magnetic field of each individual source. So let's consider a point charge Q that is moving with velocity v, located at position r at time t, or both electric field ER and magnetic field BR. That R in the bracket is just showing the position. Okay, it is not the part of the symbol. Symbol is simply B, and of electric field symbol is simply E. This R in the bracket is showing the position at which we are measuring the electric field and magnetic field. Okay, so there is a charge Q which is moving with velocity v, and it is located at any instant. If we considered it at any instant, it is located at position r, and both electric and magnetic field ER and BR exist in the space, and at that time, at that instant t, the value of electric field and magnetic field is this, ER and BR. Okay, where charge is moving. Now this is the diagram. You can see figure 4.2. The direction of the magnetic force acting on a charge particle, and the A diagram is the force on a positively charged particle with velocity v and making an angle theta with the magnetic field capital B is given by right hand thumb rule. Okay, we are going to discuss it in detail in the upcoming slides. So a moving charge particle Q is deflected in an opposite sense to minus Q in the presence of magnetic field. Okay, the force on the negative charge is opposite to that of positive charge. Okay, we are going to discuss it also. So figure 4.2 again. Now total force F, known as Lorentz force, acting on this charge Q is given by, okay, this charge Q is moving in space where both electric field and magnetic field exist, and it is moving with velocity v. So Lorentz force is given by F is equal to Q ER plus V cross B. This is cross, not multiply. It means cross product of velocity and magnetic field. Okay, so Q and in bracket ER electric field plus V cross B. Okay, and this QE, you also know QE is electric force plus Q into V cross B. This is magnetic force. If we multiply Q in the bracket, so QE is electric force and QV cross B is magnetic force. So sum of both electric force and magnetic force is known as Lorentz force. Okay, so vector sum of both these forces is known as Lorentz force, where V is the velocity of charge, R is the position of charge at any instant, ER and BR are the electric field and magnetic field respectively, and F electric and F magnetic are electric forces and magnetic force respectively. Again diagram. Lorentz force was first given by H.A. Lorentz based on the extensive experiment of Ampere and other. Okay, Ampere is also scientist, H.A. Lorentz is also scientist. So Lorentz force is named after H.A. Lorentz. So Lorentz force was given by this scientist, H.A. Lorentz. Okay, based on the extensive experiments of Ampere and other scientists. So the interaction of magnetic field with moving charge particles show following features. The magnetic force depends on Q, V and B. We have seen that what is magnetic force? Q, V cross B. So magnetic force is depending upon charge, velocity of the charge particle and magnetic field, strength of magnetic field. Negative charges experience force in opposite direction to positive charges. That thing I have also mentioned. Okay, if there is a positive charge of same magnitude, if the direction of force on this positive charge is in north direction, then if we place negative charge in place of positive charge of same magnitude, then the force reverses. Its direction will be opposite in the south direction. Okay, so negative charges experience force in the exactly opposite direction to positive charges. So magnetic force Q V cross B involves a vector product. V cross B. This is a vector product. So magnitude of vector product is given by V cross B is equal to, what is the magnitude of vector product? VB sine theta. And we are discussing about magnitude only. If there is a direction, if there is not magnitude, then direction will be there also. Okay, but we are discussing about magnitude now. Magnitude will be given by cross product. Magnitude of cross product will be given by V cross B equal to VB sine theta, and theta is the angle between V and B. Okay, vector product given above becomes 0. So vector product will be 0 when theta will be 0 degree or 180 degree. It means if velocity and magnetic field are parallel or anti-parallel. Okay, if direction of velocity and magnetic field is same or exactly opposite, then theta will be 0 degree or 180 degree. In this condition, the vector product will be 0 and hence magnetic force will be 0. If the moving charge is moving with v velocity in the direction of magnetic field or opposite direction of magnetic field, then the force experienced by that charge will be 0. Okay, magnetic force acts perpendicular to both velocity and magnetic field. Okay, so if the particle is not moving parallel to the or anti-parallel to the magnetic field, then the magnetic force that is acting on this moving charge particle will be perpendicular to both velocity and magnetic field. Direction of forces reverses if we replace positive charge with negative charge. Okay, so I have already mentioned that direction will reverse if we place positive charge with negative charge. So this is due to the change of sign of force due to negative polarity of charge. Okay, so at the place of Q there is minus Q, so sign of force will change. Okay, so hence direction of force will reverse. So direction of magnetic force is given by screw rule. or right hand rule for vector product. Okay, so what is the direction of force? This magnetic force will always be perpendicular to both velocity and magnetic field, because it is a result of vector product of velocity and magnetic field. Okay, so we know that in vector product the resultant v cross b will be in the direction of perpendicular to both the constituent vectors. Means if the v cross b, so v cross v will be perpendicular to both v and b. So you can see the A diagram. Okay, and what is the right hand rule for vector product? Align your fingers. Okay, you have to remember this rule. This rule is applicable in the whole chapter. Okay, so align your fingers of your right hand in the direction of velocity v. So you have to align the fingers in the direction of v, velocity v of the charge particle. Now curl them towards the magnetic field vector b. You have to curl these fingers towards the magnetic field vector b. Then your thumb will point in the direction of magnetic force F acting on the charge as shown in the diagram. You have to align the fingers towards velocity and you have to curl them towards magnetic field vector, and your thumb will give the direction of magnetic force. Okay, so this thumb will give the direction of magnetic force if there is a positive charge. Okay, if we replace the positive with negative, then this force will be in downward direction. Okay, so you have to remember this. So magnetic force is 0 if charge is not moving. If V is equal to 0, then magnetic field force will be 0 according to the formula. So magnetic force is given by Q V cross B, which is QVB sine theta. Okay, if it is not charged, if it is uncharged particle, there will be no magnetic force. If velocity is 0, then there is also force, magnetic force will be 0. Okay, if magnetic field is 0 in that region, then also magnetic force will be 0, or theta, if theta is 0 degree or 180 degree, then also magnetic force will be 0. So magnetic force only applied on moving charges, okay, that are not moving in the direction of magnetic field or in the opposite direction of magnetic field. Only a moving charge feels the magnetic force. The expression for the magnetic force helps us to define the unit of magnetic field. So magnetic force is given by QV cross B, QVB sine theta. Now we have not applied the mod, that means magnitude. So direction will also be there, n cap, that is the direction, and direction can be found using right hand rule for vector products, where n cap gives the direction of magnetic force and theta is the angle between velocity v and magnetic field b. If we put q equal to 1 coulomb and velocity equal to 1 meter per second, theta equal to 90 degree and force equal to 1 Newton in the above force expression, okay, then magnitude of magnetic field B is 1 SI unit. This is the definition of unit of magnetic field. So magnitude of magnetic field B is 1 SI unit if 1 Newton force is acting on 1 coulomb charge moving perpendicular to B at 1 meter per second velocity. All things we have put unity. Okay, so Q is equal to 1 coulomb, that is 1 coulomb charge, and velocity 1 meter per second. The force is acting on the charge particle is 1 Newton, and this charge is moving perpendicular to B, that is theta 90 degree. This is the value of 1 SI unit of magnetic field. Okay, so now we can see what is unit of magnetic field. Dimensionally we can see, in dimension we cannot consider the sine theta because it is dimensionless. So dimensionally B can be represented as force magnetic upon QV. Okay, so therefore unit of B is measured as Newton second, or put all the units of force, charge and velocity. You will get Newton second upon Coulomb meter. So this unit is known as Tesla, named after Nikola Tesla. Okay, so unit of magnetic field is Tesla. Tesla is a large unit. Okay, a smaller unit, that is CGS unit, called Gauss, which is 10 raised to power minus 4 Tesla, is often used. Earth's magnetic field. You can see the value of Earth's magnetic field. It is approximately 3.56 into 10 raised to power minus 5 Tesla, which is very weak. 3.6 into 10 raised to power minus 5 Tesla, which is very weak field. Okay. Now 4.2.3, magnetic force on a current carrying conductor. So this is the current carrying conductor. So there are electrons flowing through that conductor. Okay, so you can see at O point there is an electron, its drift velocity is Vd. Okay, and magnetic field is along Z axis. Okay, and force is along X axis, and drift velocity of electron is along Y axis. All the things are mutually perpendicular. Okay, A is the area of cross section and L is the length of the conductor, and I is the current flowing through the wire in the opposite direction of movement of electron. So the analysis of force due to magnetic field on a single moving charge can be extended to a straight rod carrying current. Consider a rod of uniform cross-sectional area A and length L. Inside the rod, there are mobile charge carriers, electrons here. Okay, specifically in conductors there are electrons, but we are deriving the generalized result for all type of mobile charge carriers, either it is positive or negative. So in this rod there are mobile charge carrier. These mobile charge carriers are spread evenly throughout the rod. Also, n is the number of mobile charges per unit volume of the conductor. Small n is the number density, number of mobile charge carriers per unit volume of the conductor. So to find the total number of mobile charge carriers in the rod, what we can do, multiply the electron density or mobile charge carrier density n with volume. Okay, so electron charge density small n into multiply length into area into electron density n. You will get the capital N, number of electrons in the rod. Okay, small n is the number of mobile charge carrier per unit volume of the conductor. If we multiply this with volume, we will get the number of mobile charge carriers. Okay, total number of mobile charge carrier in the conductor, capital N. Okay, small n is number of mobile charger carriers per unit volume of conductor. If we multiply it with volume, we will get the number of mobile charge carriers. So we have to find the total number of mobile charge carriers. So multiply length into area, which is volume, into electron density small n. Then the total number of mobile charge carriers in conductor is NLA. Okay. Now when steady current flows through the rod, what is steady current? Constant current. They move at an average speed called drift speed. Okay, we have discussed in detail in previous chapter current electricity that all the electrons move with average speed called drift velocity, that is Vd. Okay, in an external magnetic field B, the force on charge carrier will be F equal to NLA, which is number of charge carriers, into QVD into B. That QVDB, it is magnetic force on one electron, and NLA, that is number of total electrons or number of total mobile charge carriers. So F is equal to NLA into QVD into B, that is total magnetic force on all the mobile charge carriers, where Q is the charge on mobile charge carriers. In chapter current electricity, we saw that current density J is equal to NQVD. We saw NEVD. Okay, E is the charge on electron, but we are deriving the generalized result. So we are putting E as Q. Charge can be different from E. So NQVD. current I is equal to NQVDA. We have put the mod sign because current is scalar quantity. So we are taking the magnitude of drift velocity. So also we have seen that I is equal to J into A. What was current density? Current upon area. So current is equal to current density into area. Thus F is equal to NQVD LA into B. Now NQVD we can write it as J. JAL into B. So J into A is I. So F is equal to I into L cross B. Okay, I into L cross B. Mark it as 4.4 equation. Again cross product appeared. So here L is vector. Now L has become the vector with magnitude L, rod length and direction identical to current. So this L vector having direction same as current. So direction of L cross B is given by screw rule or right hand rule for vector product. Okay, so note that I isn't a vector, current is not a vector. We have transferred the vector sign from J to L in the last step. Okay, you can see in the last step we have transferred the vector sign from J to L because I cannot be vector. Current is scalar quantity. So B represent external magnetic field, not the field from the current carrying rod. Okay, so B is external magnetic field, not the magnetic field produced by the conductor. For any wire shape other than straight, Lorentz force calculation involves. If the wire is not straight, so what can we do? So we have to consider the small strips, small straight strips, DLJ, small length DL. So this is there is a small strip DL or J is specified strips DL1, DL2, J is from 1 to N, DL1, DL2, small strips, straight strips. So summing all the individual forces on the small strips and the net force on the wire. If wire is not straight, we have to cut out small strips on the wire that are straight. So force on all these small strips can be summed up and the net force can be given as F equal to summation J I DLJ cross B. Okay, so according to that we can sum up. We can put J1, 2, 3, the number of linear strips, okay, that we are considering in a non-linear road. So this summation typically converts to integral in most cases. Okay, so we will prefer the integral more than this summation sign. So this is the example 4.1. A straight wire of mass 200 gram and length 1.5 meter carries a current of 2 ampere. It is suspended in mid-air by a uniform horizontal magnetic field B. What is the magnitude of magnetic field? Okay, this is the diagram. So there is a rod carrying current. Okay, magnetic field is in what direction? It is cross. It means perpendicular to the plane and going into the plane. Okay, inside the plane, going inside the plane, not coming out. Okay, L is the length of the conductor. So let's see the solution. What is given? Mass of the wire 200 gram, length of the wire 1.5 meter, current flowing through wire 2 ampere. From equation 4.4 we have discussed force is given by I L cross B. Okay, so magnitude of cross product is given by LB sine theta. L cross B is given by LB sine theta. So theta here is 90 degree because current is flowing from left to right and magnetic field is inside the plane, perpendicular to the plane. So theta here is 90 degree. So F is equal to ILB sine 90 degree. So L and B are perpendicular to each other. That's why theta is 90 degree. Okay. Now direction of force can be found using right hand rule for vector products. Hence we can find there is an upward force. By using right hand rule, we have found that there is upward force F of magnitude ILB for mid-air suspension. If the wire is suspending in mid-air, That means the magnetic force is being balanced by force due to gravity. So mg is equal to ILB. Okay, the rod of the mass of the weight of the rod is balancing the magnetic force. Okay, so now we can rearrange and find the value of B equal to mg upon IL equal to 0.2 into 9.8 upon 2 into 1.5. So magnetic field is 0.65 Tesla. Note that it would have been sufficient to specify m by L mass per unit length of the wire. Earth's magnetic field is approximately 3.6 into 10 to the power minus 5 Tesla. Next question is, if the magnetic field is parallel to the positive y-axis and charged particle is moving along the positive x-axis, which way would the Lorentz force be for an electron, or B part is for a proton? So this is the diagram. Magnetic field is perpendicular to plane and inside. Okay, and charge is moving along x-axis. Magnetic field is along y-axis. Okay, so they are perpendicular. V and B are perpendicular. Since there is no electric field in the region, so Lorentz force will be equal to magnetic force. So magnetic force on the moving charge given by Q V cross B, and direction of force will be given by right hand rule for vector products. So in question, the velocity V of particle is along x-axis, while B, the magnetic field, is along y-axis, as I have already mentioned. So V cross B is along z-axis. V is along x-axis, B is along y-axis. So V cross B will be along z-axis according to right hand rule. So let's see the solution. For electron, it will be along minus z-axis, because negative sign appeared in the force due to negative polarity of the charge. And B, for positive charge, force is along positive z-axis. Okay, for electron, direction of force will be reverse. That is in the negative z direction. So there is a summary. Lorentz force is given by F equal to QE plus V cross B. Okay, magnetic force QV cross B acts perpendicular to both velocity V and magnetic field B. Current carrying conductor experiences force in the magnetic field. Force on the current carrying conductor is given by F I L cross B. Direction of L is same as current direction, and direction of forces can be found using screw rule or right hand rule for vector products. So there are some practice questions. First question, state and explain Lorentz force. How does the direction of force depends on polarity of charge? So you have to do yourself. It will be a revision for yourself. So describe how a current carrying conductor experiences force in the magnetic field. What factors affect the magnitude of the force? Third question is, an electron having charge 1.6 into 10 to the power minus 19 coulomb moves with a velocity 2 into 10 to the power 6 meter per second perpendicular to magnetic field of 0.5 Tesla. What is the magnetic force experienced by the electron? A straight conductor of length 20 centimeter carries a current of 5 ampere. If it is placed in uniform magnetic field of 0.4 Tesla at an angle of 30 degree to the field, what is the force experienced by the conductor? So these are some practice questions. You have to practice yourself. So thank you. I hope you enjoyed the session.